Hello, this is Lesson 12, Third and Higher Order Linear Constant Coefficient Homogeneous Ordinary Differential Equations. We're going to look at solutions that we can get by using the characteristic equation of these ordinary differential equations. What we're going to do is look at specifically ordinary differential equations and initial value problems that involve third order homogeneous linear constant coefficient ordinary differential equations. We're only going to look at third order, but the conclusions that we reach can be generalized to any order, fourth, fifth, or higher order equations of this type. Let us consider this initial value problem. The third derivative of y with respect to x plus a function of x times the second derivative of y plus another function of x times the first derivative of y plus another function of x times y equals 0. With initial conditions, y of x naught equals a number y naught, y prime of x naught is y sub 1, and y double prime of x naught is another number y sub 2. When do we have a unique solution to this type of problem? Well, here's one situation where we do. If those three functions, p2, p1, and p0, are continuous on an interval from alpha to beta, if this x naught that you have here in the initial conditions is in the interval from alpha to beta, and then if y0, y1, and y2 are numbers, any numbers of any values, then this initial value problem has a unique solution on the interval from alpha to beta. So the main thing to remember is when you look at a differential equation like this and you wonder if there's a unique solution, ask yourself if these three functions that are in front of these derivatives and y, are they all continuous on the interval that you're interested in? Let's talk about the concept linear independence of a set of n functions. Let's let y sub 1 of x, y sub 2 of x through y sub n of x be n functions defined on an interval I. The collection of functions are linearly independent on that interval I if, whenever, c1y1 plus c2y2 plus all the way through c sub n y sub n of x equals 0 for all x and I, we must have c1, c2, c3, all the way through cn, all are equal to 0. In other words, if this is equal to 0, then all of these constants, multiples of these y functions, all these constants have to be 0. That's the only way to make this thing equal to 0. Let's talk about the concept of a linear combination. A sum of the form c1 times y1 of x plus c2 times y2 of x plus c sub n times y sub n of x, where these c's here are constants. This is called a linear combination of the functions y sub 1, y sub 2, all the way through y sub n of x. Here are a couple examples. If I look at this expression, 3 times y sub 1 of x plus 9 times y sub 2 of x minus y sub 3 of x is a linear combination of y sub 1, y sub 2, and y sub 3. Here the c1 is 3, the c2 is 9, and the c sub 3 is a minus 1, because this last term could be written as plus minus 1 times y sub 3. Let's look at another example. Suppose we just have y sub 1 of x plus y sub 3 of x. I claim that is also a linear combination of the functions y sub 1, y sub 2, and y sub 3, because we could write this equivalently as 1 times y sub 1 plus 0 times y sub 2 plus 1 times y sub 3. So let's rewrite the definition of what it means to be linearly independent, a set of functions being linearly independent. the set of functions y sub 1 of x, y sub 2 of x, through y sub n of x is linearly independent on some interval if the only linear combination of them, c1 times y1 plus c2 times y2 plus all the way through c sub n, y sub n, equaling the zero function, is the trivial linear combination. The trivial linear combination is where all of the constants are zeros. 0 times y sub 1 plus 0 times y sub 2 plus all the way through 0 times y sub n. On the other hand, we can talk about sets of functions that are not linearly independent. And we have a term for that also. If the functions are not linearly independent, we say that they are linearly dependent. Let's look at a couple of facts about polynomials. Suppose z of x is equal to ax squared plus bx plus c. So this is a function defined by this quadratic formula. And suppose that z of x equals 0 for all x. Then these coefficients, a, b, and c, all have to be 0. So let's see how we can prove that. Since z of x is a constant function, especially it's a zero function, then z of x, z prime of x, and z double prime of x all are zero functions. Remember that the derivative of a constant function is 0, and so that's why z prime and z double prime are zero functions also. So in other words, this equals 0 for all x, z prime of x equals 0 for all x, z double prime of x equals 0 for all x. So let's look at z of 0. We know that has to be 0, but using this formula for z of x, we get a times 0 squared plus b times 0 plus c equals 0, and that tells us that z equals 0. If we look at z prime of x, what is z prime of x? Looking up here for a second, it's going to be 2ax plus b. So z prime of 0 is going to be 2a times 0 plus b. Well, z prime of 0 is 0, so 2 times a times 0 plus b is 0. That tells us that b is 0. Similarly, if we differentiate this twice to calculate z double prime of x, z double prime of x is just going to be 2a. So z double prime of 0 being 0 tells us that 2a is 0, which tells us that a is 0. So if you have this quadratic polynomial equaling 0 for all x, all of these coefficients that appear in that polynomial have to be 0. It's easy to extend this result to third degree, fourth degree, and so on polynomial functions. And so we'll just state this fact. If you have an nth degree polynomial equaling 0 for all x, then all of the coefficients up here, a sub n minus 1, a sub n minus 2, all the way through a sub naught, all of those have to equal 0. We're going to use these two lemmas. A lemma is kind of like a small theorem, a statement of fact that is not of, I guess you can say, not tremendously hard to prove and often is used to prove other things. So these two facts we're going to use, actually the one down here mainly, to consider some situations where certain functions, sets of functions, are linearly independent or dependent. As an example, let's consider three functions and determine if they are linearly dependent or independent. So y1 will be x squared plus 5x, y2 of x will be 2x squared minus x, y sub 3 of x will be 3x squared plus 3x, all of these defined on minus infinity to infinity. These are polynomials, so they are defined everywhere. Are these three functions a linearly dependent or linearly independent set of functions? So for the solution, let's look at an arbitrary linear combination of these, c1y1 plus c2y2 plus c3y3 equals 0 for all x. Let's suppose that's true. And let's ask if that implies that C1, C2, and C3 all have to be 0 or not. Well, let's substitute in what y1, y2, and y3 are. So here's the substitution. So this equals 0 for all x. And now let's collect terms. We have a c1x squared here, plus 2c2x squared here, plus 3c3x squared here. We can write that part as c1 plus 2c2 plus 3c3 times x squared. And then we have some x terms. C1 times 5x, C2 times minus x, C3 times 3x, and that gives us 5c1 minus c2 plus 3c3 all times x. And notice there's no constant term here, and we can write that as 0c1 plus 0c2 plus 0c3, and all of this is the same as all of this. It equals 0 for all x. So what we know is if we have a polynomial that's 0 for all x, the coefficient of x squared in this one has to be 0, the coefficient of x has to be 0, and this constant term has to be 0. So we set all three of these equal to 0, solve for c1, c2, c3. If the only solution is the trivial solution, that c1, c2, and c3 are all 0, then the three functions are linearly independent. Otherwise, they will be linearly dependent. So here's the polynomial equation that we found before. This stuff equals 0 for all x. This coefficient equals 0, that's right here. This coefficient of x equals 0, that equation's right here. This coefficient of 1, basically, this constant term, is also 0. So C1, C2, C3 have to satisfy this system of three equations and three unknowns. So here's what we'll do. We'll use sage math in this case to solve these equations. It could be done by hand also. So we'll define the augmented matrix A, and that is in this line of sage math, this command in this cell. And then we'll see what A is, and here it is. Notice that the first row, 1, 2, 3, 0, corresponds to what we have here. The coefficients 1, 2, 3, and 0, the constant on the right-hand side. This second row of A comes from the second equation, similarly, and this third row of A comes from this third equation. So this gives us our augmented matrix for this system of equations. Then we find the reduced row echelon form of this matrix. We could do that by hand by starting with this matrix and using elementary row operations, but there's a built-in command to do that. A dot RREF for reduced row echelon form, and then there are parentheses here too. When we execute this line of code, we get this matrix. This matrix, if we think of it as corresponding to a system of linear equations, has the same solution set as the matrix up here, this augmented matrix. So we think of this as an augmented matrix and ask what are its solutions. Well, if we look at it, the first row here gives us this equation. The second row here gives us this second equation. The third row just says that 0c1 plus 0c2 plus 0c3 equals 0. That doesn't really give us any information about c1, c2, and c3. So we really just have to focus on these first two equations. We have leading variables c1 and c2, and we have a free variable for c3. And so what we can do here is we can set c3 equal to some number. I think I'll set c3 equal to 1, and then I'll solve for c1 from this equation, solve for c2 from this equation. So c1 is minus 9/11ths and c2 is minus 12/11ths. So here I have three values, c1, c2, c3, and they're not all 0. So that tells me that there is a non-trivial solution to this equation. I can let C1, C2, and C3 be the values that we found up here. So that tells us that y1, y sub 2, and y sub 3 are linearly dependent. So we now have this equation, C1 times this stuff plus C2 times this stuff plus C3 times this stuff equals 0 for all x between minus infinity and infinity. If you look at this, it is a polynomial equation. We saw that a solution that will work in this case to make this 0 for all x was C1 was minus 9/11, C2 was minus 12/11, and C3 was 1. Let's just check to see if that really works. So let's plug these numbers in for C1, C2, and C3 up here, and that's where we get this. C1 was this, C2 was this, and C3 was 1 right here. If we look at the x squared term, we have minus 9/11 times x squared here, minus 12/11 times 2x squared here, plus 1 times 3x squared here. And so that's going to be what times x squared? Minus 9/11, minus 24/11, plus 33/11. Then if we look at the x term, we have minus 9/11 times 5x, and then minus 12/11 times minus x, and then plus 3x here. And that gives us the x term down here with the coefficient minus 45/11 plus 12/11 plus 33/11. Now, if you look at this, what do these two coefficients turn out to be? Well, minus 9 minus 24 plus 33 is 0, so this is 0x squared. And minus 45 plus 12 plus 33, the coefficient of x, is also 0. So we get 0x squared plus 0x. So these three numbers can be used to come up with a non-trivial solution to C1y1 plus C2y2 plus C3y3 is the 0 function. And since we do have a non-trivial linear combination of these functions equaling the 0 function, that tells us that those functions are linearly dependent. Let's look at an example that is just slightly different. Let's let y1 equal this function, same as before. Let y sub 2 of x equal this, same as before. And let's change y sub 3 slightly. Let's let y sub 3x be 3x squared plus 7 on the interval from minus infinity to infinity. Are these functions linearly dependent or independent on that interval? So we'll start the same way as before. Suppose C1 times this function plus C2 times this function plus C3 times this function equals 0 for all x between minus infinity and infinity. So then if we collect x squared terms, we get this stuff times x squared. Collect the x terms from these and you get 5c1 minus c2 times x. And there's only one constant term, c3 times 7 is 7c3. So we want this polynomial to equal 0 for all x between minus infinity and infinity. And so what can we do in that case? Well, I guess I wrote down the same thing here as we had before. And if this polynomial, something times x squared plus something times x plus something times the constant term equals 0, the only way that can be true is if this coefficient is 0, this coefficient is 0, and this term equals 0. So that gives us three conditions that C1, C2, and C3 have to satisfy. Now the question is, do these three equations require C1, C2, and C3 to be all 0. If the only solution is the trivial solution, then these excuse me, functions that we started with are linearly independent. So what we have to do then is to find all the solutions to these three equations. So we need to find the solution set to this system of linear equations. We'll do it using built-in matrix functions. First of all, the augmented matrix for this system of equations is the following matrix right here. If you look at the coefficients on this first equation, 1, 2, 3, and the right-hand side 0, that's what we have here in the first row, 1, 2, 3, 0. Similarly, this second equation gives us the second row. This third equation, 0c1 plus 0c2 plus 7c3 equals 0, is this last row, 0, 0, 7, 0. If we apply the reduced row echelon form function to this matrix, we get this matrix. And the solution to the system of equations corresponding to this matrix equals the solution to the system of equations corresponding to this matrix. The matrix and its reduced row echelon form correspond to equivalent systems of equations that have the same solution set. But if we look at this matrix, it's basically C1 equals 0, C2 equals 0, and C3 equals 0. So the only solution to this system of equations up here is C1 is 0, C2 is 0, and C3 is 0. So that tells us that the functions that we started with, which are the three that we see down here, are linearly independent. And 0 times this first function plus 0 times this second function plus 0 times this third function is the only linear combination of those three functions that is equal to the 0 function. Let's consider this third order linear homogeneous differential equation. I claim that there are three linearly independent solutions to this equation, and I will not actually prove it, but I will display how we can find those three solutions. I'm going to look at three separate initial value problems. We'll let y1 be the solution to this initial value problem here. We have that third order linear homogeneous differential equation and initial conditions on the value of y, y prime, and y double prime at some number x naught. And the values of these are 1, 0, 0. The second initial value problem will let y2 be a solution to this, and the same differential equation, but if we look at these initial conditions, instead of 1, 0, 0, we have 0, 1, 0. Let y3 be the solution to this initial value problem, and the only difference in this one from the above ones is right here, 0, 0, 1. It turns out, and theory supports this, there are proofs of this, that if P2, P1, and P0 are continuous on an interval I, and if x0 is within that interval I, then there are solutions to these three problems, and the three solutions we get to these three initial value problems are linearly independent. So let's talk about the solution space to this third order linear differential equation. From the previous slide, we looked at three initial value problems involving this same differential equation. And what we can say is that these three functions span the entire solution space. If we want to know what all the solutions to this linear homogeneous third order differential equation are, then we can find all of them by taking linear combinations of these three functions. If we look at all functions that can be formed as a linear combination of these three, we find all solutions to this differential equation. So we can say that these form a basis for the solution space to L of y equals 0. If you've had linear algebra, you've talked about bases and you've talked about vector spaces, and that's basically what's going on here. So we can also say, in terms of vector spaces, the dimension of the superspace for this equation is 3, because it takes three functions, which we can think of as abstractly vectors, that form a basis for this space. And once you have one basis for a solution space to L of y equals 0, any other basis for the solution space will have the same number of functions in it. Any three linear independent solutions to L of y equals 0 will be a basis for the solution space. Notice we said 3 here, the dimension is 3. You need three linearly independent solutions to span all of the solutions by looking at linear combinations. Less than 3 will not do. So what we can say then is that the general solution of the ordinary differential equation is the following linear combination: c1 y1 of x plus c2 y2 of x plus c sub 3 y3 of x. And this holds whenever we have three linearly independent solutions, y1, y2, and y3. When we say this is the general solution, we're saying that this equation represents all the solutions. By picking different values of c1, c2, c3, we would get different solutions to the differential equation up here. So in this equation, which we think of as the general solution, we can think of c1, c2, and c sub 3 as being arbitrary constants. So let's consider this third order differential equation, homogeneous, linear, where we have constant coefficients. a3, a2, a sub 1, a sub 0 are just constants like 3 or 4 or minus 2. So it's constant coefficient, linear, and homogeneous. We have 0 on the right-hand side. We know that this equation is going to have three linearly independent solutions. And the question is, how do we attempt it? Well, the same way that we did in second order equations. We look for solutions of the form y equals e to the rx, and in that case, substituting that in, we can find the characteristic equation that r has to satisfy, and it's a sub 3r cubed plus a sub 2r squared plus a sub 1r plus a sub 0 equals 0. Polynomial equations can have roots of multiplicity 1 or 2 or 3 or higher. And for the characteristic equation, we have a polynomial equation, and if we have, let's say, some real solutions to the characteristic equation, what sorts of linearly independent solutions to the ordinary differential equation can we get in that case? Well, here's what we can say about real solutions. To each real solution, r equals a number lambda to the characteristic equation, we get the following types of terms in our solution, and these terms are solutions to the homogeneous problem, and so by the superposition principle, linear combinations of those terms would also be a solution to the homogeneous ordinary differential equation. If lambda has multiplicity 1, then e to the lambda x is a solution to our ordinary differential equation. Well, that would be a single root, not a double root or triple root, just multiplicity 1. If we had lambda being a double root, the multiplicity would be 2. You can also have a triple root or more. If lambda has multiplicity k, then e to the lambda x, xe to the lambda x squared e to the lambda x, through x to the k minus 1 e to the lambda x are a collection of k linearly independent solutions to that ordinary differential equation. So if we're writing out the general solution, In this case, we would have a linear combination of all of these types of functions. And so our solutions to the ordinary differential equation theoretically could have many terms. What about complex? So let's look at the complex root case. For each pair of complex conjugate solutions, R equals A alpha plus or minus I beta to the characteristic equation for our ordinary differential equation, we get the following types of terms. We may get the following types of terms in our solution. If alpha plus or minus I beta each has multiplicity 1, and what I mean by that is alpha plus I beta is a root of multiplicity 1, alpha minus I beta is also a root of multiplicity 1. So this would be two solutions to the characteristic equation. Well, in that case, we have two functions here which are solutions to that constant coefficient ordinary differential equation, and they are linearly independent. Suppose we have alpha plus I beta having multiplicity k, and alpha minus I beta is also a solution of multiplicity k. So that would be solutions with, I guess you can say, a total multiplicity or of 2k there. We would expect to have 2 times k solutions that are linearly independent to our ordinary differential equation. And here they are, 2k solutions, k solutions in each of these lines. E to the alpha x cosine beta x, xe to the alpha x cosine beta x, all the way through x to the k minus 1 power e to the alpha x cosine beta x. All of these are solutions to the ordinary differential equation. Also, if you replace all these cosines with sines, these are also solutions to the ordinary differential equation. And all of these are a linearly independent set of solutions to that differential equation. Now, for a given differential equation, constant coefficient, homogeneous, linear, you might have some roots of the characteristic equation that are real and others that are complex. And what happens is for each real root, we have some solutions that we saw on the previous slide, solutions to the ordinary differential equation. And for each complex root, we also have some more solutions to the ordinary differential equation. And if you put them all together as a linear combination, you would get the general solution to our ordinary differential equation. So let's look at an example. Here we have a fifth order homogeneous linear constant coefficient differential equation. Looking at these coefficients of the fifth derivative, the fourth derivative, third derivative, and so forth, we can immediately see that the characteristic equation is going to be 2r to the fifth minus 22r to the fourth plus 84r cubed minus 108r squared minus 54r plus 162 equals 0. Okay. Now, we want to find the solutions to this equation. One way to help us is to graph y equals this polynomial in R. So over here we have a graph. Think of the horizontal axis as being the R axis. Vertical axis is the y axis. Goes all the way up to 200, pretty big number. And here is the graph of that polynomial. From here, it looks like the polynomial crosses the x-axis at -1 and perhaps touches the x-axis right at 3. It gets down here, getting closer and closer to 0 until we get to 3, and then it seems to increase again. So we guess that r equals -1 and r equals 3 are going to be solutions to that characteristic equation, that polynomial equation. And if you graph a little bit more, you'll find out that those seem to be the only places where this graph touches the r-axis. Now, the thing that we're graphing over here is fifth degree. So there should be 5 solutions to this equation, counting multiplicities. And if you play with it for a little while, you can figure out that the characteristic equation does factor into 2 times r plus 1 times r minus 3 to the 4th equals 0. So from this factorization, we can see that r equals minus 1 has multiplicity 1, and r equals 3 has multiplicity 4. Okay, so for the root minus 1, we get a term in our solution, c sub 1 e to the minus 1 times x. Now for the solution 3, which has multiplicity 4, we get 4 solutions that are linearly independent. c2 e to the 3x plus c3x e to the 3x plus c4 x squared e to the 3x plus c5 x cubed e to the 3x. So this is what our general solution to that differential equation looks like. If we had an initial value problem, we would have to use those initial conditions to figure out what C1, C2, C3, C4, and C5 are. Let's look at another example. Let's consider the following problem. Find the general solution to 4 times the 4th derivative of x with respect to t minus 8 times the 3rd derivative of x with respect to t plus 42 times the 2nd derivative of x with respect to t minus 104 dx dt plus 69 x of t equals 0. So this is a constant coefficient linear homogeneous differential equation. Now, once again, from this differential equation, we can immediately read off what the characteristic equation is. 4r to the 4th minus 8r cubed plus 42r squared minus 104r plus 69 equals 0. Now, this is a 4th degree polynomial equation. There actually is a method, there is a bunch of formulas for what the solutions to a 4th degree polynomial equation are. But they're very complicated. Almost nobody uses them these days. So what we're going to do is to try to find out what the solutions are to the characteristic equation by using computer methods. We're going to use Sage Math. So the first thing we'll do is graph y equals 4r to the 4th minus 8r cubed plus 42r squared minus 104r plus 69 equals 0. And here is the graph. The horizontal axis is the r-axis, and the vertical axis is y. Okay, notice that this graph does not seem to touch the r-axis, this horizontal axis, anywhere. If you graph this further, you'd find out that it just keeps going up and up and up. In that case, we know that this polynomial equation has 4 solutions, but none of them are real. If we had a real solution, we would see this graph crossing the horizontal axis at that number representing the real solution. So all of the solutions have to be complex in this case. Solving a 4th degree equation, as I mentioned, is kind of hard to solve by hand. And so what we're going to do is to resort to computer software to solve this algebraic equation, the characteristic equation, and then we will use those solutions to find the general solution to this ordinary differential equation. So we will use Sage Math to figure out how to factor that polynomial. So let's declare r to be a variable, And then let's solve the equation r to the fourth minus 8r cubed plus 42 times r squared minus 104 times r plus 169 equals 0, and we're going to solve it for r. We have the left-hand side of our equation here, and implicitly we're solving when this expression equals 0. And what happens is we find when we execute this by typing Shift-Enter, we get two distinct solutions to this equation. 2 minus 3i and r equals 2 plus 3i. These are complex conjugates of each other. Notice that our equation is of fourth degree. So that means we should have, counting multiplicities, 4 solutions. The only way that can happen when these roots come in complex conjugate pairs is if the polynomial factors this way. R minus 2 minus 3i, that quantity squared, and the quantity r minus the quantity 2 plus 3i, that whole quantity squared. And so we have complex conjugate roots, each with multiplicity 2. So that means that we're going to have a solution that looks something like this. Since we have solutions of 2 plus 3i with multiplicity 2, we're going to get a solution e to the 2t cosine 3t. We're also going to get e to the 2t sine 3t. But it's multiplicity 2, so that also means that we're going to have a t e to the 2t cosine 3t term, and also a t e to the 2t sine 3t term. Now, you might ask, didn't I get all of those by just looking at this one solution? Well, that's true, but what we have are two solutions. Each is complex, and on our previous slide we saw that if we have this root and this root, both of multiplicity 2, this is the type of solution that we're going to have for these 4 solutions that we get from our polynomial equation. 1, 2, 3, 4 solutions here. C1, C2, C3, C4 are arbitrary constants, and so this comprises the general solution to our ordinary differential equation. So let's look at another example. Let's solve this differential equation. Find the general solution. The third derivative of x with respect to t minus 3 times the second derivative of x with respect to t equals 0. So what's the characteristic equation going to be by letting x equal e to the rt? What we find is from this we get r cubed minus 3r squared equals 0. That's the characteristic equation. Both of these terms you can factor out an r squared from them, and so this characteristic equation factors into r squared times r minus 3 equals 0. So r equals 3 is a single root, and r equals 0 is a double root. So in that case, our solution x of t has to look like this. It's going to be c1 e to the 3t, since 3 was a single root, plus c2 e to the 0t, plus c3t e to the 0t, since r equals 0 was a double root. So we got this first term in our general solution from r equals 3 being a single root. We got these two terms in our general solution because r equals 0 was a double root. Now, let's remember that 0 times t is 0, and e to the 0 equals 1. So what we have here in this line can be simplified to c1 e to the 3t, which we have here, plus c2 times 1, which is just c2, plus c3 times t times 1, which is just c3 times t. So here is the general solution to this differential equation. Thanks for watching this video. I hope you found it educational and somewhat entertaining. So this concludes our study of constant coefficient homogeneous linear differential equations. We found that to solve these differential equations, all the solutions depended on first finding the solutions to the characteristic equation, which could be a quadratic equation, a cubic equation, or even a higher degree polynomial equation, depending on the order of the differential equation. Next, we're going to see how this can help us solve certain non-homogeneous problems. We're not going to have equals 0 on the right-hand side anymore. We're going to be considering something slightly more complicated.